Okay, so good afternoon. Thank you for coming. I hope that the number of students will not decrease drastically after you hear the first lectures. So I suggested to give a course on strategic games, but this is normally a topic which belongs to the economics. However, at certain moment, perhaps 15 years ago, computer scientists discovered the subject, and they, in some sense, adopted this, and it became part of a quite intense research area in computer science, which is now called algorithmic game theory. And computer scientists added to the topic a number of new directions, but one still studies certain things which started much earlier. And in fact, at the very end of this introductory lecture, I will quote a theorem which is more than 100 years old. So my idea was to divide these lectures in such a way that I'll first give you, for free, an introduction to certain games which economists learn during the first year of economic studies. But this will be after the break. Before the break, my idea was to give you an idea what is the landscape of games so that you understand where those strategic games fit and what are the other alternatives. So this is the basic overview of this talk. So I will provide you with a standard classification of games. It's not exhaustive because it's a topic really which grows in some sense. The most two important parts are games which are cooperative and non-cooperative. But for some reason, one uses different names, usually coalitional games and strategic games. And there is a special case of strategic games called zero-sum games, which is such a popular concept that I occasionally even see it in a newspaper, once even on a first page. And another special case of strategic games are extensive games, of which a best example is chess, for instance, or checkers. And these extensive games don't need to have the feature of chess that there are only 3 outcomes. But there is a very special category of such games which are called win or lose games. And for the more narrowed the class of games, the stronger results you can prove. And for some classes of games, certain results became classic. So I feel my moral obligation is to provide you with such an introduction that you have enough information so that when there exists a cocktail party, you can easily discuss these topics in such a way that you will pretend that you studied a couple of years of economics or, for example, mathematics, because all these concepts, they come back. And all what one needs to know are essentially the main results which one can achieve. So I will continue with this classification. So it's a never-ending story. You should start perhaps by reading the bottom line. There is a kind of ongoing project which is called Handbook of Game Theory, and until now 3 volumes appeared, and in total it has by now 62 chapters. And there are other handbooks which appear, which are related to game theory. So it is very difficult to provide some exhaustive classification because games are essentially about interaction. And there are various forms of interaction, and only, let's say, you may come up anytime with some new proposal, and it can be then called a game. So I will just start by mentioning these cooperative games, which are, as I mentioned, usually called the other way around. These are coalitional games, which are usually called cooperative. And some typical examples are, I will be more specific in a moment, is that suppose that some project has to be financed, and how do you divide the costs? So this is called cost allocation. Another is how to deal with financial problems. And a good example is bankruptcy. So some company went bankrupt, how to divide the money among the claimants. Bargaining, so negotiations, also can be viewed both actually as cooperative and non-cooperative games, because the idea is that you want to achieve an outcome which is satisfactory to all parties. And that is exactly the purpose of bargaining. Now, voting is also an example of a coalitional games. So one can formulate it without any problem as a special game of this form. Now, non-cooperative games, the most strategic ones, the most famous one is Prisoner's Dilemma, which also appears occasionally on the first page of a newspaper. I remember I live in the Netherlands, and I remember that there is a weekly magazine called Elsevier, and they somehow came up a couple of years ago with an idea that they will rank hospitals. And they rank hospitals by asking each hospital to rank the other hospitals. And from this, they make a list and they say, this is the ranking of hospitals. And actually, they started to use it also for various departments of universities. Now, it is a very problematic approach. And there was one director, a director of one hospital, who decided to state his opinions. And he said it's a prisoner's dilemma for us to deal with it. And it ended up on the first page of a daily to which I'm subscribed. So I was amused to see, and I was wondering whether he knows what is prisoner's dilemma, but after this you will see that probably he didn't know. So this is the most famous game, and I'll discuss it so that you can impress your colleagues already as of tomorrow what it is, because it is something which is so prevalent that if you are obsessed, you can see everywhere Prisoner's Dilemma. I'll give you several examples from, let's say, our daily life. Extensive games, I mentioned chess is a good example. There are also repeated games. You play the same game on and on. And then even this is not general enough, because there are some games which can be played infinitely often. The idea is that you accumulate what you gain in a game just by adding. In first game I earned, I don't know, €3, in the second 5, in second round, so you accumulate it. But if you add to it inflation, then you can also even accumulate things over an infinite amount of time. So this is a division which makes sense, and for each category there are different results. Now, an increasingly important topic in both economics and algorithmic game theory is auctions. And one of the reasons is that this is the main income, for example, of Google and many other advertising agencies, which offer slots. And these slots are offered on the basis of some interaction between the provider and the user. And this interaction, the best way to settle it is by offering a specific auction. And it's a very huge topic. Okay, so voting also can be viewed as a non-cooperative game, but there are many other categories. For example, stochastic games are games which are repeated, but every new round has different characteristics, and these characteristics depend on the previous one, but not in a deterministic way, but there is some probability. So these games also have this feature of being finitely or infinitely repeated. Now there is an important class of games called evolutionary games, which were proposed actually by a biologist, John Maynard Smith. And then they started to be very intensely studied by people who both know game theory and biology, and this is sometimes considered as the most successful application of game theory, where one tries to view evolution as a special case, as a special type of games. So now I will continue by giving you some idea of coalitional games. So the point is that these games have a certain purpose. So the purpose is that people want to achieve something together. And one of the issues is that there is some profit which is generated or some costs which have to be paid. And the question is how to divide it. And there is an approach which is very important, axiomatic approach, I will mention to you. And also one can look this in a larger perspective to try to understand what are, in quotes, the rules of the game. So I will give you some example. Suppose that there is some village, and there are 3 villages, and there is some water available, but one has to, yes, oh, you had a question? No. So one wants to connect these villages to this water supply. So these villages are at some different positions at some random places, and now the company which agrees to provide the water connection, this is perhaps a good signal for others to switch off. I did it. You can check. So my point was that the company came up with some paying scheme. And they said if only one village, namely village number 1, gets connected, then you have to pay 12. The village 2, suppose that it's on a hill, has to pay 15. The third one also 12. But if villages 1 and 2 together propose to get connected, then they only have to pay 19, and so on. And if all 3 villages agree, then they have to pay 26. So suppose that this is what happens, and now the villages decide that they will, all three agree that they will be connected to the water supply. Question: how much each of these villages is supposed to pay? Now, you have some, if you did not have these first 2 lines, you would say, of course, everybody has to pay 1/3. But it's obvious from this data that these villages are not identically positioned with respect to this water supply. So a question arises what to do. And this is exactly one of the purposes of the coalitional or cooperative games. So one introduces a concept which is called a core. And a core is a set of ways of allocating costs. And it has to satisfy 2 conditions. One is that it has to be efficient. That is to say, you add up all these costs, and then you get the cost which equals to the cost of the whole group, which is called in this context grand coalition. Then there is something called group rationality. And the group rationality is that there is no group which will say, sorry, I don't want to participate in this deal. We get out and we get a separate agreement with the company which supplies water, which is intuitive. And let us see now an example. So suppose that I provide the following scheme for payment. I say that the first village has to pay 8, the second 10, and the third 8. Now one can ask ourselves, is this a good deal? Now what does it mean? Because the village 1 and 2 could get together and they could say, let's see, if we don't go with the village 3, we decided to go only by ourselves, then shall we get a better deal? Well, the answer is no, because if you add 8 and 10, you get 18. But if they only decided to get connected, ignoring this third village, they would have to pay 19. So for them, there is no reason to go separate. And you can check that this is the case for any other group or coalition. And this way, you know that this scheme makes sense. Now, the second one, I claim it is not a good way of dividing the total costs. You see that it all adds up to 26, which is the cost for all 3 villages. But which 2 villages would consider that it's not a good deal? I don't see. Sorry? Exactly, because if they would ignore this deal, they could come up with a better solution. If they would just have gone separately, they would pay only 19. So this is the informal definition of a core. Now I will give you a formal definition. So this is a formal definition, literally copied from one of several books on game theory. So first one introduces a concept. So there is a finite number of players. Their set is called usually grand coalition. And then a coalitional game is extremely trivial notion. It is a mapping which provides to every coalition, so every set of players, some number, with the restriction that the empty set gets 0. That's all. You cannot imagine a simpler definition. And the idea is that this number corresponds to what this group can generate together. Now, on a previous slide, I didn't talk about what profit they can generate, but what they have to pay. But this is easy to retrieve because one can define, given a cost-sharing game, which was on the previous slide with this water supply. So given such a scheme of payments, one can turn it into a game by assigning to a coalition C the following expression. We first check how much each of these participants have to pay separately, and we deduct from it the cost of this coalition itself. Now, the intuition is that this is the gain which coalition C can achieve if they act together. Because if they act separately, it is this first term. And if they act together, it's the other one. So the difference is how much they can gain. So this expression is meant only to transform the previous slide into this terminology. So efficient allocation is just as I mentioned on the previous slide in this context of costs. Every player achieves something, so some payoff. And these payoffs have to add up to the payoff which is generated by a grand coalition. And we just introduce a natural notation in this context that F from S is what coalition S will get under such a payment scheme. So now group rationality says that there is no group which will get out and consider that they have a better deal. So this means that what the group can generate, which is F from S, is at least as good as they would get if they just act on their own. So this is that the group is interested in participating. So this was an example with cost. Here it is with those values, but it is the same. And the core, which is the set of such allocations that nobody has incentive to leave, is simply an allocation, so this assignment of how much everybody gains, such that it covers, the sum covers what the whole grand coalition achieves, which is this line. And additionally, this allocation satisfies group rationality. So given such a definition of a coalitional game, one just comes up with the concept of core and says that this is what is relevant. Namely, this provides you with a set of ways of dividing the profits of a grand coalition among people in such a way that everybody will be interested, and you could argue that this is the only meaningful way. But this is just one proposal, and this is what makes game theory interesting, that you sort of are allowed to come up with concepts, whatever you want, and then you just see whether it is more popular or not. So here is another concept which was proposed by Shapley. I will come back to him in a second. So allocation function, we just mentioned what it is, allocation in a game, and allocation function takes one coalitional game and says, aha, this is the allocation in that game. So it is one level up. And Shapley value is an allocation function phi, which satisfies three properties. He introduced it in 1953. So this is at the bottom. So for any two players, if they, in a game, now we are interested in a game which is identified by small v. Every game, as you remember, had just one characteristic, namely this function v. Now for I, vi from v is simply how much this allocation gives to player I in the game v. So this first expression, which is here, says that I have to move this every now and then. So this says the following. Suppose that in game v, players I and j are actually contributing the same to every coalition. So if a coalition C wants to adopt and thinks, shall we go for I or shall we approach J? It turns out that no matter what coalition is selected, they face the same problem, that these two players offer the same added value. So then this function has to assign to these players the same value, the same number. Dummy says that if you have a player who does not contribute to any coalition, so you choose a coalition when a player is not present, you add him to this coalition, and now you wonder, does this make a difference? Suppose that this player I has this strange property that for no coalition he makes any difference. So that's why he's called dummy. And dummy player, by definition, should get 0. This is a most problematic axiom which he proposed. So you take two games, and plus means simply, you can guess, these are functions, so it's adding two functions. So it is a new game in which you get the gains which are, so to say, computed in each game separately. And he argued that this allocation should be additive. So if you take such a sum of the games, then this distributes across this addition. So a value function is a function which associates with every game some way of gains, which for each game adds up to the value of grand coalition. So let me summarize these definitions so far. On a previous slide, we had one allocation. It was here. But now we parameterize this allocation by a game. So this game is an argument of this phi. So phi has a subscript, which is the player, and the argument, which is the game. So what happens here is that we have a set of axioms for such a general function which in each game should behave in a meaningful way, according to the three axioms. And Shapley proved that there exists exactly one function which has such properties. That is to say, if we agree that these are the axioms, the way we should assign values to players in each game, then there exists only one solution. And this was a result which started a huge line of research which continues until today. And people came up with different axioms, and even most remarkably, there are now characterizations of this Shapley value, this is called Shapley value, which consists of just one axiom. So instead of 3, there are characterizations with 2, but even with 1. And most problematic was this last axiom. There was no obvious reason for adopting it, but these alternative definitions dispel this doubt. Now I come back to Shapley. For this very contribution, Shapley got a Nobel Prize in economics. He also did some other things, but these are important ones. But these ones are considered, this one is considered the most important thing. So now you learned of contributions which translate into a Nobel Prize. And why is it important? Because the purpose of cooperative games is to understand how we should divide profits, of how we should jointly pay for projects. And there are no obvious rules, and this definition of core is in some sense problematic. Namely, for some games, there are plenty of potential solutions which belong to the core, and in some games, core does not exist, whereas the Shapley value always exists. The problem is that Shapley value does not have to be in the core. So this starts, of course, another line of research, of finding games for which it always belongs in core, etc. But the main point is that there is some tangible way to defend a scheme. So suppose that some electricity company decides on charging customers. And then somebody starts to protest, why should I pay that much and the other that much? If you have a good explanation, and this explanation is clear and well understood and well studied, then of course it is something which is acceptable. And indeed, this has been used in some applications also concerning the costs of water supply. And it is a huge area. So this is all what I plan to say during this course on coalitional games. And the reason I stop here is because I promised to tell you what are strategic games. But one can appreciate the difference only if one knows what are the alternatives. So here we go from now till the end of the course about strategic games. So what is the purpose? The purpose of coalitional games was how to decide about, say, sharing the costs. But here it is, the objectives are different. So the objective is to understand what competition, what is the effect of competition, can you predict the outcome of competition, and can you determine what are the best outcomes? So I'll just go through these points. So first is how to model it. So you will see that the model, which is called a strategic game, is very natural. Now one can also assume something about behavior of the players. So economists have this marvelous word, and they say a rational player. Now, because there is apparent, I guess, no economist here, then let me tell you, the correct way is to say not rational, but egoistic. So the point is that every player only thinks about himself, and he wants to maximize his profit. So economists have those nasty, nice, lofty words. For this, they use the word rational. Now, you can ask yourself whether, if people are egoistic, whether it is good for society. And the answer is sometimes. And I will show you some shocking examples. So you can also start to wonder how to achieve them. And then there are those special cases, which I mentioned on perhaps the first slide. The more limited the game, the different and more specific results you can obtain. So in particular, in zero-sum games, obviously, one is interested whether any of the players has a winning strategy. All this can be explained within the context of strategic games. But there are people who study zero-sum games. They do not know even what I will tell today because they don't need it. because it's a field which is so specialized that one only focuses on the issue of these games, and what I say is not needed. It provides you with a kind of umbrella over a topic where this fits. And where is the difference? The difference is that in zero-sum games, there are 2 players. And in general, in strategic games, there is an arbitrary, finite, sometimes also infinite number of players. So 2 players is a special case, and then the zero-sum is a very natural special case. So here is a game of Prisoner's Dilemma. Who has heard of Prisoner's Dilemma? Excellent. And who understands why it is a dilemma? Are you sure? Okay, so let's check. Because there are several ways of looking at it, and in some sense it's a topic which is, I will come back at the end of this slide, which it is a never-ending topic. It is an internal dilemma because you cannot solve it. So here is a game. Now somebody can ask oneself, what do you mean, a game? Well, I will tell you, this is something which is called bimatrix, which is a natural and intuitive way of representing games for 2 players. So there are 2 players, Mr. Rowe and Mrs. Column, and they play together by choosing simultaneously a strategy. Each of them has the same strategy, and there are 2 possibilities. One is C for cooperate, D is for defect, or actually it should be B for betray. So each of them chooses a strategy simultaneously, and this bimatrix tells what are the payoffs. So for example, if Mr. Rowe chooses C and Mrs. Column chooses D, then Mr. Rowe gets 0 and Mrs. Column gets 3. Did you see how I got it? I just looked into this square. Because Mr. Rowe chose C and Mrs. Column D, so we ended up here. So this is an elegant way to encode the game in a very compact way, and we can easily refer to this. Now there are several assumptions about it. First of all, the players know the game. So you should think that we choose 2 people from the audience, and they are Mr. Rowe and Mrs. Column, and they see the game on the screen. And this is the game they are supposed to play. So everybody knows everything, including that the other player is rational. And they together are supposed simultaneously to choose their strategy. So now everybody can choose at the same time. So obviously, ideal solution would be everybody chooses C because they get 2 each. However, the paradox is that every rational player will choose D. As a result, they will get payoff 1. And that's the paradox. Now, I can guess that if you didn't understand the paradox, you still don't understand it, because I just said the formal definition. But now let us think how come what I just said. So one needs to understand certain concepts, but these concepts I will explain in a second, focus on the game only. So you understand how it is played. People, both of them, see this game, and they have to take at the same time decision. So let us analyze each player separately. Player Rowe has 2 options. Now, should he choose C or D? Well, let us look. We know what he gets. These are called payoffs. If he chooses C, he gets respectively either 2 or 0. If he chooses D, then he gets either 3 or 1. So D is obviously better for him. And the same is for the other player because it's a symmetric game. So this Mrs. Column has to choose between C and D, and it's exactly the same. If she chooses C, we look at the second position. She gets either 0 or 2 or 0. But if she chooses D, she gets either 3 or 1. So no matter what the other player chooses, it's always better to choose D. As a result, each of them will choose D because he knows or she knows that in such case, it will always yield to a better payoff. Yet, when they choose D together, they end up in a situation which is certainly not the optimal one. Namely, they should have chosen C. And you can say, aha, because they did not understand what the game is about, so let's explain them the game. Now, the game was already explained. What is, they also, this what I told you, one can tell them and say, listen, this is prisoner's dilemma. Do you understand, guys? And now you play the game, but now you understand what are the consequences. They again will make the same decision. And that is the dilemma, that no matter how long you discuss it, it will always remain, this argument which I presented will remain valid. Now, you can ask yourself, what has it to do with our lives? It is everywhere, this prisoner's dilemma. Think about the, I can give you some example which a colleague gave me. Suppose a couple decides to divorce. And each of them thinks, I will take a lawyer. But now the idea is that they want to have a better deal. So they have, each of them has two options. Either to get a lawyer who is cheap, but not so good, or an expensive lawyer who is very good. So each person thinks, I rather choose the better lawyer because he will provide a better deal. The other person thinks the same, and they both end up with the better lawyer more expensive, and they don't gain anything. Because if each of them chose a cheaper lawyer, they would still get the same deal because these lawyers would be equally good under the assumption, and still the difference would be in paying for the lawyer. Now the arms race is a more serious example. Ideally, the countries should not arm themselves. It costs money. Okay, America would think that it's good for our business and whatever, but it is a useless way of spending money. So you could say, two countries, say India and Pakistan, you tell them, listen, you should sit at the table and discuss. It is useless for you to arm yourself against, this is your main enemy, is just across the border. Why bother? So you present all the cases why it is not useful to be involved in arms race, and still it does not change anything. Why? Because it is an example of prisoner's dilemma. I can give you another example which contributes exactly these numbers, which when I gave this course to students, then I prepared some chocolates, and then I said that there are two options. I chose two students and say there are two options. Either if you say cooperate, then this means give 2 chocolates to the other person. And if you say I defect, then it means give me 1 chocolate. So now, if you think of these two students, then each of them should ideally give the other one 2 chocolates, because each of them will end up with 2 chocolates. No, because each of them will think, aha, if the other one says give the other one, so me, 2 chocolates, I additionally claim give me 1 chocolate and I get 3 chocolates. I'm better off. This is that this row student would say, I choose D, the other one chooses C, so I end up with 3 chocolates. So this is exactly, so if you are altruistic towards the other and it's reciprocal, then you get the best outcome, but life is different. So now to discuss these matters, we can introduce certain concepts, but this example provides a good intuition for this. So first is a best response. So given what the other players, here there is only one, chose, I suppose that I know what they chose. So we break the rules. They first decide and then I decide. So I can think what is best for me. So for example, here we agreed that D is always best no matter what the other one chooses. So this is the official definition, best response. Nash equilibrium is a concept where each of the players chose a best response with respect to what the others did. Informally, the formal definitions on this next slide. Informally, it is as follows. Suppose that all of you play some game, which, say, I explained on the blackboard, and you have to take decisions simultaneously so that it is a strategic game. And then after the game finished, you looked at this payoff table, you decide, did I make a good decision? So suppose that I ask one person, each person separately, are you satisfied with what you chose? Are you satisfied? And if everybody says yes, then we have a Nash equilibrium. Because it means that if I say, are you satisfied? It means implicitly, given that the others don't change what they chose. So if I put this question to each of you and everybody says yes, then we have a Nash equilibrium. But there is another concept which is more important, one would think, is social optimum. And social optimum means that you have a joint strategy, so a selection of strategies, one per player, such that the generated income is maximum. So this is the aggregate payoff. So using this terminology, we can say that in this prisoner's dilemma game, we have, you can check, a unique Nash equilibrium, namely defect, whereas the other important combination, CC, is a unique social optimum. So here is a formal definition after this introductory example. So we have a game for some fixed number of players. Each player has some set of strategies, and then we also have a payoff function which ties all of them together. Because look what happens. Payoff for player I gets as arguments all strategies. Therefore, these players are intertwined in what they will get. And that's where this interaction comes in. So incidentally, we assume there are at least two players. If there is one player, it's called optimization theory, because then you want to maximize certain outcome. But now you want to maximize it over more players, and it's not obvious what to, let's say, focus on. That's why those points which are of interest, like social optimum and Nash equilibrium. So here are again those assumptions, and these assumptions can be the first, simultaneously they choose the decisions. As on the previous slide, each player is rational, egoistic, and there is also a concept that they have common knowledge, so they know what the game is played, but moreover, they know that everybody else knows it, and that everybody else knows that everybody else, etc. It goes ad infinitum. And this is an assumption which, incidentally, I open a bracket, leads to a concept of which is well defined in modal logic, and one also at certain moment connected this with game theory by proving that if the players have common knowledge of rationality, which is the case, that not only of the game, but also of that they, each of them are egoistic, then certain outcomes of the game will follow. So this is the definition, and now the main concept. So it is the same what I said on the first slide by using a notation. Now all what you need to remember as a notation from this slide is S minus I. So S is a joint strategy. A vector of strategy is one per player. But if I want to focus on the opponents of player I, then I write S minus I. So if I have two players, then S minus I is the other player, okay? So this is a very important way of writing, and this first line is relevant because you will get used to certain conventions. So Si and S prime I are typical names for strategies of a player I. Now, if we take a vector of strategies, it is called joint strategy, so it's usually denoted by S or S prime, but, and this is important, also with this Si, comma, S minus I. Now, it is an alternative way of writing S. So every mathematician would say, what a nonsense, but it is a very nice convention of writing S in such a way that we focus temporarily on player I. And this very notation is already appears in the formal definition of a best response. So we focus on player I, we say that his opponents fixed their strategy, so S minus I is fixed, and now we think what is best for player I. So of course he has his payoff function to the side, so in that case we say that Si is a best response if for any alternative, including say this Si, he won't get better off. He won't get a better payoff. And this statement here provides us with the criterion. So it can be the same, but it cannot be better. And Nash Equilibrium is exactly what we said before, but now written formally. For each player and for each strategy of his, this strategy entering S, because it's a definition that S is a Nash equilibrium, the strategy entering S for player I yields for him at least as much as any other strategy. And the intuition is, as I said before, that no player can gain by unilaterally changing his strategy. And social welfare, which is an additional concept, is useful to talk about social optimum. We just aggregate the payoffs for a given strategy over all players. And this function, called social welfare function, its maximum, it's called social optimum. So these are the only definitions you need. And now, just to refresh your memory, again, prisoner's dilemma, but now we play it for n players. And now these numbers will start to make sense, because sometimes when you study mathematically a limited case, you don't see what's going on. Here you see what is going on. There will be two strategies, but there will be now numbers. So 1, it was before C, and 0, D. And the payoff function is defined. All what I need to do is to determine players, so there are n players, strategies, 0 or 1, payoff functions, here it is. So this payoff function has a characteristic that if he chooses defect, then he gets one more than if he chose cooperate. So if you look at this function, you can forget the C and D, you see that it's always better to choose 0 because you get higher payoff than the other one. And you can double check that for these numbers, for n equal to, you get the original game I discussed. And if you add up those numbers, so this would be the number of players who selected 1 among the opponents of player I, correct? So now this FET1 and FET0 are those crucial joint strategies. Because what happens here is that 0, one can check, is a unique Nash equilibrium. It is the unique situation that no player will gain by deviating. Let us check. I mean, I claim it. Now, is there anybody who can tell me why it is so? Looking at the payoff function. You knew prisoner's dilemma, so you have the... Yes, so if everybody chose 0 and we focus on player I, he also chose 0. So if he chose 1, he would get how much more? No, the payoff will be 1 less because he chooses, he has 0 and he says, oh, no, I will choose 1. Then his payoff drops. So point is, one can easily check that this all zeros is the only Nash equilibrium in this game, because for every player it's better always to choose a 0, because it's always this is bigger than that. But if each of them chooses 1, then you get the optimum, social optimum. Then all these payoffs are 2 times here n minus 1 plus, this is this one, 2 times n minus 1. That will be the payoff for each player. And there are n players, so the social welfare will be 2n times n minus 1. And you can check this is the only social optimum, and the other is the only Nash equilibrium. So this easily generalizes to more players, and it in fact provides a better understanding of the problem. So now about Nash equilibria, we have plenty of games, and in many games there are no Nash equilibria. I'll give you in a moment some example. But there are also many games, one I will study, it's called congestion games, where there are always equilibria. And also in those games which are finite but where you take turns, they are called finite extensive games, there also always exists Nash equilibria. So now here is an example, it's called Matching Penny, a game which does not have Nash equilibrium. Is there any volunteer who can explain me why it is the case? Yes. But the strategies are the same, you mean? Because the payoffs are always different. One will always get 1 and the other minus 1. Yes, correct. Yes. Yes. Yes, so informally, in every outcome, there is one player who is not happy, the one who lost. And he can always win by changing to the other strategy. That's how it is done here. So in Polish it's called orzeł czy reszka. So this is a game which head is for orzeł, for reszka, head or tail. So this game has no Nash equilibrium. And this is important to remember. So Nash equilibrium allows you to understand the game, but how do you understand this game? Now, what does it mean to understand the game? The answer is that we can predict what will be the outcome. In this game, you can't predict. So this is one of these problems which we'll address in a moment. So here I go to explain to you a contribution of Nash. Who has heard of John Nash? Okay, good. So he had a remarkable life and also died in a remarkable way. Namely, he received the most prestigious award in mathematics for people who are above 40, which was called Abel Prize. And he flew back to New York, and with his wife, they took a taxi from the airport, and the taxi driver caused an accident, and they both died, not the taxi driver. So this happened, I don't remember, a few years ago, but he was a person who was on a fast track to become a mathematician who would get a Fields Medal, which is the most prestigious medal for the condition is to be younger than 40, but being around 30, he became mentally sick. He had a persecution mania and schizophrenia and was several years closed in mental asylum. There is a book and a film, which Terrible Beauty, which was based on his life. And then eventually he got better off, and people in economics who were all the time using his results. This is one of 2 or 3 most fundamental results which he obtained. Started to press that he should get Nobel Prize. And he got Nobel Prize for economics in 1994, I guess, or 3. And he was one of 3 recipients. Another one, by the way, had this with these chocolates for children, if you remember. So it was Aumann who came up with this simplest solution or explanation of prisoner's dilemma. And in this book, there is a very good fragment that all people were terribly afraid that when he will come to Oslo to obtain the Nobel Prize, that there will be to Stockholm, because that's where the prize in economics is given, that he will compromise himself by his ludicrous behavior, but fortunately everything went fine. And he received very heavy medication. And since he got better off, he never produced anything of any value, but he was still invited to many conferences. And I even attended one of his lectures. It was a total disaster. And moreover, what is said, it was a common knowledge. Everybody in the room knew that it's nonsense. And there was room full of very, let's say, 2 or 3 other Nobel Prize winners in economics. Everybody knew that it does not make sense at all what he's talking about. But out of respect for him, everybody was playing a game without agreeing before, so that he would not feel that he talks about ridiculous things. So it is a tragic story, but he got this result when he was 21 or 22. And it is a result which is, the proof, the paper is 1 page long. I have it on my memory stick, I will show it to you. It's very simple, the proof. It just uses some theorem in topology. So the main burden is a theorem in topology, but the proof is really immediate. And the point is that he came up with this idea, and this idea provides the main way to look at a game and to try to predict what a game can have. And his result says that it's true, not all games have Nash equilibria, but certain natural games built out of the games I showed you until now do. And how these equilibria are built? Well, you just use so-called mixed strategies. So intuition is very easy. Suppose you have a number of strategies, but you are not certain what to do. Think that this is like money you want to invest in some funds. So you just say, okay, I bet 30% on this strategy, 20% on this, and how much is left? 50% on this strategy. And this is called mixed strategy. So you sort of spread your bets over the original strategies. So now you create for every player a larger set of strategies which are infinite, because formally each strategy now is a probability distribution over the given set of finite strategies. In this larger game, where everybody has infinitely many strategies, you have a unique natural definition of a payoff, which will be a kind of canonic extension of the original payoff. You just check these things appropriate for the probabilities chosen. So I just made here an example to illustrate how come that matching pennies does have a Nash equilibrium in this extension. So we have those mixed strategies, which is simply, I write it in such a form, alpha times h plus what is left times t. And the payoff function is simply what so we have some 2 strategies, M1 and M2, M for mixed. For player 1 and player 2, everybody, each of them has different probability. And now the payoff is computed as follows. You look at this matrix and you say, what's the chance that the game ends up in the upper left corner, H. Well, it depends on the probabilities. So the chance for the first player to choose it is alpha 1, for the second is alpha 2. So the chance that the game will end up there is alpha 1 times alpha 2. And this is what we get here. And what will be in that case the payoff for player 1? Well, that's what the original function says, namely the payoff n1 from HH, which we incidentally know is 1. So then you go over all four possibilities. So here the chance to end up is still alpha 1 for player 1, the row player. But for the other one, it is 1 minus alpha 2. So you get this payoff. And you add it up. And this is a well-defined function, which is a payoff for a player, in this case for player 1, in this extended game in which you have mixed strategies, so infinitely many strategies. And it turns out that in this game there is a Nash equilibrium, not surprising, where everybody bets 50% on each strategy. And in that case, you can easily compute that the payoff will be 0, which is logical, because if none of them regrets, that means that they, so to say, are in symmetric situation, and it always adds up to 0, because such a mixed extension of a zero-sum game is zero-sum game, which is easy to check. So the summary is that this is the Nash equilibrium of this game in mixed strategies. So I use the same concept, but applied to a bigger game. And so Nash result is, I come back now to this, that if you start with a finite strategic game, you build this mixed extension. This, what I did, was a special case. And in this mixed extension, as again this question, is there a Nash equilibrium? The answer is yes. Of course, he did not talk about Nash equilibrium, he talked about general equilibrium points. But this is the important theorem, which also shows that it is a concept which very often does appear, but you have to be more liberal what you choose as strategies. So now I go on, start to narrow the scope, and now talk about zero-sum games. So zero-sum games were the games which were studied until Nash started, so before 50s. Until 50s, there were essentially no results about games for n players. So von Neumann, who was considered by many one of the most brilliant mathematicians of 20th century, who also contributed to the creation of the first computer, was also involved in the Manhattan Project, the aim of which was to construct the atomic bomb. So it was a marvelously versatile mathematician. He also had a model which was used later to study neural systems, and several most unusual and informative contributions. And he also got interested in economics. And he teamed up with an economist called Oscar Morgenstern, who was not so good in mathematics, which was not difficult. And the book which they wrote became a book which is still today used as a kind of classic, which was called Theory of Economic Behavior, in which they introduced coalitional games and strategic games, but for strategic games, essentially, they focused on zero-sum games. So on zero-sum games, before this book was written, von Neumann, he emigrated to United States, so he still published this paper while in Europe, in German, and this book appeared when he was in Princeton, in, I think, early 50s. So the result appeared in the book, but was first established in that paper. So the result was 4 zero-sum games. Now you can guess what it is. 2 players, the payoffs add up to 0. And he proved the following result. Now we talk about mixed strategies. So M minus I is the strategy, mixed strategy chose by the opponent of player I. So it here doesn't matter whether it's player 1 or 2, and this shows the advantage of this notation. You don't need to write for player I1 this, for player 2 one formula. So this explains the name, min, max, max, min. Now, you can ask yourself what it is and why is it important. This is called, this refers to certain strategies which are called saddle points, and it is as follows. If you look at a saddle, then it has this shape, that this rider on a horse will sit in it, but also that shape. And therefore, you have a three-dimensional structure which has an intersection kind of this structure or three-dimensional object and that one. And this point in the middle has the property that if you move along this coordinate, you only go up, but if you move along this coordinate, you only go down. And this result says that it doesn't matter in what order you do it, whether you first choose the minimum and then maximum or the other way around. And this looks like an uninteresting formula, but what is behind this formula, it turns out that it identifies a pair of strategies, and these strategies form Nash equilibrium. Of course, at that time, Nash was not perhaps even born, I suspect. So this was called an equilibrium point. But the results which were obtained here are that equilibria points, so Nash equilibria in today's terminology, consist of pair of strategies which have a certain form. And each strategy is called security strategy. And the good intuition is that suppose you are a paranoid player and you think that the other person knows what you want to choose and he wants to punish you. So you are very suspect and you only choose such a strategy which minimizes the damage caused by the malevolent behavior of the other person. So this is a security strategy for paranoiacs. And it turns out that every combination of the security strategies forms a Nash equilibrium, and these are the only Nash equilibria. This is an explanation of this result in today's language. So, moreover, the payoffs are the same. Okay, so here is a very short summary of pseudo-historical survey. The first game where there was some interaction in the form of strategic interaction was proposed by Frenchman Cournot, and it's called Cournot competition. After break, I hope I'll reach the point that I'll tell you what it is. And this Nash theorem generalizes, this is another point, one specific aspect of this Nash minimax theorem because it's for n players. And as I said, Nash proved this using a specific result in topology. Then he came up with a slightly longer, still very simple proof using a more known result called Brouwer's fixed point theorem. So this is just sort of information that you can impress friends at a cocktail party. It's on this level, okay? So now I continue, but I will suggest it's a good moment for a break. Okay, so I resume. So my idea was actually to proceed faster. The only solution is that I can talk faster. So I hope that now that you returned, you have no way to leave the room. I forgot to lock it actually, but I will now try to be faster. So I move now to something which is called extensive games. I will not discuss this in the lectures that follow, but it's good to know because there is a direct connection with strategic games, but still it's a different topic. In Prisoner's Dilemma, the issue was that the players were taking their decisions, choosing their strategy simultaneously. But there are many games, and in fact that's what we think intuitively what is a game. they take choices in turn. So they alternate, like in chess or checkers, their decisions or their current move. And this is called an extensive game. And you can translate or transform every strategic game into an extensive way in a very simple way. So look, above we have the original definition of Prisoner's Dilemma, and below I have it played as an extensive game. So first we say to player row, you make a decision, you choose a strategy, and then there is a second round where the second player takes a decision. So this tree, a decision tree, shows how the game proceeds. So if player 1 starts, then let's say the player row is player 1, then he chooses either C and D, and then the player 2 starts, and he can choose either C and D, and then we get those outcomes. So this game is now written out as an extensive game. Idea is obvious. So now let us jump forward. What I showed on the previous slide was a game for 2 players, and the game had 2 stages. Now, in general, there can be several players and more stages. Just think, let's say, more stages you see in chess, but you can imagine easily games where more players are involved. And just like in repeated games here, the game can even proceed infinitely long. The point is that you have to define what's the outcome of the game, but it can be just the path which follows, but you can associate the payoffs, as you do here, and then assign inflation, and these payoffs will then add up to a finite number. It all can be done. And what we will allow in what follows is just a simple special case, but which shows certain type of options already explicitly. Finitely many players, but each player may have infinitely many choices. So we can also play a game with mixed strategies as an extensive game, where players had infinitely many strategies. And there is a very important concept, I'll just mention it briefly, of perfect information, which means that each player knows what were the previous moves. You can easily imagine a game which does not have perfect information, like I didn't play poker since I was a student, so I don't remember. I think one puts some cards on the table, but I do not know which cards the previous person put. So in that case, it is not a game of perfect information. So a formal definition of a game with perfect information is as follows. You have a game tree, you saw a simple example, and this game tree is a game which at each node we know which player moves. So there is a function d, for some reason called, which assigns to each node except the leaf of the tree a player who is supposed to choose a strategy. So this is this function d. There is a set of leaves which are called z, and the outcome function assigns to each leaf a payoff for each player. So this is here an example. This function which assigns here to the leaf of each tree the payoff to each player, this is what is now called an outcome function. And the outcome function and this plus this turn function determines the game. And how do the game proceeds? So how does the game proceed? So it starts at the root. Then the player who controls the root, so d of root is the number of this player, he takes a decision and the game starts to move down the tree. So given a node, we have a set of possible continuations for a given player. So here essentially the game takes place on a graph, and the player at each node chooses which edge to continue. So I now, incidentally, the definitions, if you open a typical book on game theory of these games, you get a headache. I know a book where the definition has from A to I, so through all the letters from A to I, that there is this set and this and this function and so on. All what I do here is I try to make it as intuitive as possible. So we now have to identify, determine what the players do when they choose a certain edge. So we say that this will be the strategy. But sometimes the strategy has to be distinguished from the name of the edge, so there are many unneeded details. So I just make it a bit informal, if you will see, if you forgive me. Still, the definition is complicated because now we have to say what is a strategy of a player in a game. Think of it informally. Suppose that you play chess against a computer. Now, what does it mean? That this computer knows in every single situation what move to do, what move to make. So this will be the strategy of the computer. So how do you define a strategy of a computer? For every situation where the game we know, so we have this huge tree, suppose chess is finite, according to the rules of FIDA it is. So you have this gigantic tree, which is given, so to say, and now you, as a person who writes this computer chess program, have to determine what the computer does. So in every situation in which it's computer turn, this program should mention which move to make. So the strategy which is generated by this computer program is a recipe how to move. So here is the definition for player I, a strategy, which is exactly this. It is a function given is this tree of the game. And then a strategy for a player says that in every node where it is his turn, he knows exactly how to move next. So this is the second bullet or triangle. And the function is defined on all nodes where it is the turn of player I, which is defined in the first bullet. So if I take a vector of these strategies, I get something called joint strategy. And this is now sounds too familiar to the previous situation when we discussed strategic games. And you will see in a moment that it is, in fact, a special case of strategic games, but one has to prepare some definitions first. So if you have a strategy for each player, then the best way to think of it is that you have a chess game played between two computers. So each computer program, between two computer programs, each program has exactly prescription how to move. You team you put them together, they play against each other, there will be an outcome of the game. Now, how do we proceed? Well, we just check which path in this huge tree will be selected. So there is a path, a finite path, this tree is finite, which corresponds to this joint strategy, one strategy for each player. And we simply proceed down this path. If we reach a certain node, we first check whose turn it is. And since we have his strategy in this tuple, then we consult what does the strategy say, what move should the player do at this specific node. Once we reach the bottom, then we apply this outcome function, which was before. It is the function in the second bullet. And this function provides for each player a payoff. So this way, we obtained a payoff, and this payoff is called the outcome of the game. In this case, outcome of this joint strategy. So, given this, here is matching penny, and here is a game extensive game. It corresponds to this matching pennies game. And you can see here the strategies for player 1 and player 2. The strange thing is that now the player 2 has more strategies than before. Now, how is this possible? Well, because we simply follow the definition. If player 1 begins, he has only two options, head or tail. But what was the definition of a strategy for a given player? For every node which he controls, the strategy says what he should do. Well, player 2 controls two nodes, and therefore in the left node, he will have a strategy, for example, which says go left. In the right two, he could have a strategy which says go right. Here, by chance, I chose, in both cases, left. So the outcome is that for player 2, actually, I should not have said the word outcome because it was a reserved word. So the upshot is that for player 2, there are four strategies that he plays in both nodes. He controls H. In first one, he chooses H, and the other T, then T and H, and T and T. So that's why we get four strategies for him. And this, what is marked here in fat, in bold, is the joint strategy, where I marked what strategy is chosen by player 1 and what strategy is chosen by player 2. For player 2, I had to mark for each of these two nodes what he chooses. Okay, this starts to look more and more like a definition of strategic game. And in fact, with every game, extensive game, we can associate a strategic game as follows. We already know what are the strategies. They were just defined before. One line reminder, it's a prescription for a player what he does at each node he controls or she controls. We still need the payoffs. Well, that's easy. If you have this vector of strategies, so a joint strategy, we just explained that such a vector, joint strategy, results in a path through the tree. This path yields a single leaf. At this leaf, we can apply the outcome function and we get the payoffs for each player. So, to summarize, I have here a strategic game because I defined what are the strategies for each player, and I also said what are the payoff functions. Namely, it is what this outcome function provides for each player in the node which is reached by this joint strategy. So now you can use this observation to define what is a Nash equilibrium of an extensive game. It is simply a Nash equilibrium of this translation into strategic game. So here is an example because it is easily misunderstood, because it can go on forever, this kind of transformations, which is therefore a bit misleading. We started with the strategic game, yes. Yes. These are games with perfect information. I mentioned this before. So we have here matching pennies, and under it is this extensive game which corresponds to this game played in two stages. But now I go back to strategic games, but I do not get the same game. I get the game which is here. You remember that in this matching pennies, the player 2, so the column player, had 4 strategies, while the first player, the row player, had 2 strategies. So here is the strategic game which corresponds to the game in extensive form. And in this game, there are 2 Nash equilibria, whereas in the original game, there was no equilibrium. Now, here, what happens is that we talk about different game, and therefore these translations are not mutually inverse. But it is important to understand it And there is another thing, one would say, okay, so take chess and make a strategy game out of it. Now, this on paper looks fine, but in practice it's hopeless. Because these are such astronomical numbers, you cannot make any progress by this translation. But this provides you with some kind of perspective what the previous notions mean in this new framework. And Nash Equilibrium is a two-week concept here. So the right concept, which is more appropriate to talk about extensive games, is obtained by first introducing the notion of a subgame. So imagine that you have this tree, which corresponds to the game. This, I hope you understood. And suppose that we now start to play this game at a certain node. So already something happened, but from that moment on, the game proceeds downward. And how you reach this is essentially not relevant, because you know from that node, if you reach a leaf, you know what are the payoffs. So you can trim everything to this smaller tree, and you get a smaller game. The official name for it is a subgame. So such a subgame is anchored in a certain node, which is not a leaf. And then you can, in this smaller game, consider what are the strategies. There will be always truncations of these bigger strategies, because now a strategy only needs to say what you do in this smaller tree. But if you had a bigger strategy for the whole tree, then it also tells you what you do in the smaller tree. So each strategy of a player in a bigger tree induces unique strategy in the smaller tree. So if we have a joint strategy, so the sequence S1 to up Sn, and we have here we consider, is this an interesting joint strategy, then a crucial definition is that it is subgame perfect equilibrium. That's the definition. If the truncation of these strategies in every subgame form a Nash equilibrium. So it is a stronger concept than Nash equilibrium. Namely, it is not only Nash equilibrium in the original game, but in every subgame it becomes also a Nash equilibrium after you limit it. One can find easy examples of games where in some subgames you do not have Nash equilibrium, while in the original, this extensive form, you do. So in short, informal summary, that something is called subgame perfect equilibrium if in every subgame this joint strategy yields a Nash equilibrium. And there is a very important algorithm which is called backward induction, which generates this type of equilibria. And it is something which is used in one way or another because it's connected to something called minimax, and it is used in all those computer chess programs. The problem in computer chess programs is, given a situation, how do you evaluate it? So this is, from this you look forward, it's called look ahead, and then eventually while you stop looking forward, you still have to assign some value to a player in a given situation. So from this you go backward and you say, aha, so you should choose in this original situation such a strategy that you will end up at the promising point. So this is a more formal definition based on this admittedly vague concept. We start at the bottom and we try to reconstruct how the game could have proceeded. So we start at the bottom. These are the leaves. Then you choose arbitrary node whose descendants are only the leaves. You choose such a node, and this is this V here. And then you check whose turn it is to play. And you wonder, suppose the game ended in this spot. what strategy will this player choose? Well, the one which gives him the best outcome. So for each descendant of the strategy, which will be a leaf, we choose such a descendant that the payoff for player I, which is controlled by this function outcome with subscript I, is maximal. So we say that the strategy for player I, we didn't build it completely, at least in this node, his choice should be, he should choose this W. And then we remove all the other strategies. And before we do this, we also, because that is the player I who controls this node, this ultimate not leaf node, he gives no choice for the other players because it's his turn. So we know that if the game ends up there, that is the payoffs which they will get. So we determine for this node that this will be the outcomes. And we move this game one up because what happened was that if you recall, the outcome function was defined only on the leaves. Now I move this one floor up. So I remove, let's say now the outcome function is already defined on one node more. And I remove from this set of possible moves in this game the ones which started in this selected node. Because this one I already, so to say, ticked off, I know what will happen. So I remove the leaves before, under it. And I now know in that node, this player will make this move. Now I go to another node with the same property that all its descendants are leaves. I do exactly the same. And each time I do it, I just erase the successor. So this tree gets smaller and smaller, and the same procedure is all the time repeated. And each time I still have one more node, then I still have to determine what to do. Eventually, this whole tree gets one node, and we finished. What did we do? At each node, we said what each player has to do. So I, in fact, generated the joint strategy. It was done in a very piecemeal way. And also, it was not so that first I did strategy for player one, then for player two. I built it together in an interleaved fashion by treating each time the player whose turn it was to move. And this way, I built laboriously, going through all the nodes, a joint strategy for all players, because on each node, we now know who is playing. And this choice results in a unique path, which leads to a certain leaf. And in this leaf, we know what are the payoffs. But there are more than one joint strategy which is generated, because the player whose node we selected has a number of possibilities in general to maximize his outcome. And this means that this algorithm generates a set of strategies and not only one. What happens? We generated a set of strategies. And there is the following result. Now, this what I discussed, this algorithm is in the last bullet. So first of all, every extensive game has a Nash equilibrium. More specifically, we translate extensive game into a strategic form. This was the one where for matching pennies, you got this 2x4 matrix. Each such game has a Nash equilibrium. So it was no wonder that there were Nash equilibria. But it is much more important that each such game has a subgame perfect equilibrium. And now comes the relevance of this algorithm, which I showed on the previous slides. It generates those subgame perfect equilibria, and usually these results are presented as follows. One says, Selten proved that every finite extensive game with perfect information has a subgame perfect equilibrium. Proof, the backward induction generates it, and then it's not difficult to prove. But it is only part of this story. And strangely, when I started to look through the books which I had, I found only one book where it is explicitly stated that it is also the other way around, that every joint strategy generated by this backward induction is a subgame perfect equilibrium. Then I even discussed it with a colleague, and we came to the following interesting conclusion. Economists do not know algorithms. So they have a problem to reason about something with such an algorithm, especially if there are here two non-deterministic statements which are encoded in this choose. And as a result, they do not have natural means to talk about this. We computer scientists know that we can discuss some invariants, some termination criteria, and so on. So for computer scientists, it's much easier to understand what goes on. And we can easily formulate what we want to prove and somehow argue. And in these economics books, this algorithm is usually expressed in English and not in some algorithmic notation. And it's very difficult to argue about something which is explained in English. It becomes a hand-waving proof. Most of these proofs are, for my standards, not acceptable. But the problem is that all these things are for economics students easy to understand, but they don't get a course in any, let's say, algorithmic notation. So for them, it is something difficult to understand. Okay, so since I started to mention who got Nobel Prize, etc., so Selten got Nobel Prize with Nash and Aumann in '94. And this was one of the main contributions, not only because he contributed also to this evolutionary games for biology, but things which from perspective 50 years later look so obvious turns out to be very simple and intuitive. But the problem is that we absorb this knowledge and we understand where it comes from. To come up with these concepts is a different story, but it also shows what progress economics made in terms of mathematical background. Okay, so now the last part of this introductory remarks, win or lose games. These are special type of games, extensive games, where the only possible outcomes, you remember these were those payoffs at the leaves, are 1 and -1, that one person won, the other lost, like with this matching pennies. So now this opponent notation is still holds. There is only one opponent, so opponent of player I is -I. And now we have a crucial concept which does not make sense in a more general context of a winning strategy. Now, a winning strategy is the one which, no matter what the opponent chooses, you always get payoff 1, which is here So what happens here is that the definition says that SI is a winning strategy for player I if no matter what the opponent chooses, so any S prime I, the payoff for player I is still 1, which is just formulating in these concepts what everybody would guess. And this does not make sense in more general context, because what is 1? I mean, it just is a number. But if there are only 2 outcomes, then this 1 starts to mean something. And there is a theorem, in the meantime 105 years old, which says that in every win or lose game, there is a player who has a winning strategy. Which, let's say, forget that there is a draw in chess, which suppose that there is, in case of draw, you say that the winner is the black, the one who played with black. So this says in chess there is a winning strategy. In fact, this result improved towards the, let's say, to cover chess, says that there is one player who has a strategy which guarantees him at least a draw. Now, the question is, find it. So this is the problem which shows the difference between theory and practice. But the proof of this result is amazingly simple. It is a tautology. And I will show you this proof here. And this will make you think, because you think, what a deep theorem. In chess, there is at least there is a player who can guarantee at least a draw for himself. It is a tautology. And here is the proof. So first, the game, you can imagine that this game as a tree has a very arbitrary shape. But let's make this shape that it is very regular. The tree is binary, of course, because there are two players. And we can assume that the players take turns. This is not required in the definition, correct? It was not said that they have to alternate. But we can impose it. For example, imagine that in chess, there is some variant that you can make several moves. So now how do you, let's say, you can easily restore it by sort of, from such a game, making a game where everybody changes, for example, by inserting after every move a phony move of the other player, which consists of pushing the clock. Okay, that's his move. It does not change anything in the original distorted version of chess, but it is a game where they alternate the moves. So you extend this game in such a way, and you also, by adding such dummy sort of moves, make that this game is of a certain depth, and that this game ends when the second player moved. So the depth is even. So you have, by adding such dummy moves, a tree, which is a complete binary tree of depth 2k. And now I write a sentence that player 1 wins after 2k stages. I write it using quantifiers. So it is the following formula. There exists, forgive me for embellishing this boring formula, there exists a marvelous first move of the first player. No matter what the other player does, x2, read, I have a great response, which is x2, his answer was y2, so that no matter whether what y2 he chooses, I have still a fantastic response x3, and so on, such that something holds. And what is the statement here? That the player wins after that he has this statement says that the player wins after 2k rounds, so after 2k stages. So this formula formalizes this sentence. Now, the player has a winning strategy, was this formula. And now the player 2 has the winning strategy, is the formula which says that no matter what the player 1 chooses, I have a great response y1, such that no matter what x2 he chooses, I have a fantastic continuation y2, so and so on, that he loses. And as a result, we have two formulas. One, which is sentence W, which says that player 1 wins always after 2k stages, and the other one that the player, that player 1 has a winning strategy, because this W, I should have said it, is a statement that player 1 wins after these stages. So we have one sentence which says that player 1 has a winning strategy, it is phi 1, and phi 2 is the statement that player 2 has a winning strategy. And you can check that the disjunction is always true. So as a result, either player 1 or player 2 has a winning strategy, and that's the whole proof. So it makes you think, because what turns out is that we do not grasp the consequence of a statement that somebody has a winning strategy. In terms of quantifiers, it's just a formula with alternating quantifiers. And if you reverse it or you negate it, you get a statement that the other one has a winning strategy. Okay, so this closes my, with some delay, a lecture which I had in mind as an introductory lecture, which gives you some kind of landscapes of games. So we talked about coalitional games, then strategic games, then extensive games, but I said these are also games about competition. So as a result, we have again a situation where these extensive games are actually games in which are in strategic form. And then those win or lose games were special cases of strategic games. And there were also zero-sum games on the way. So as you see, as we moved from the general definition of the extensive games, we were getting smaller and smaller classes of games, but for each of them we could prove specific results. So now I'll go back to the concept of strategic games, and for this we move to the second set of slides. So the definitions of Nash Equilibrium and social welfare we had, I just had them to remind, so I'll skip. Then I'll discuss three simple games. One of them is Prisoner's Dilemma, second is Matching Pennies. There will be a couple of new examples, so let's move on. So this is the reminder of the definitions in case you do not remember. So what is strategic game? The notation with this S minus I. What is best response? What is Nash equilibrium? And what is social optimum? Ready? Okay, next. So here are three games. Two you already feel familiar with. Now there is a third one, which is called Battle of the Sexes. It's some pompous name for which has the following story, that a man and a woman want to go either to a box fight, F is for this box fight, or for ballet. So now guess who prefers what. So if here, the question I have to you is who is man, who is woman? Which player is woman? Perhaps you will, as a woman, tell me which player is a woman in this, according to this intuition which we usually have. Is the question clear? So here is the game. Sorry, I asked her. You know these things by heart. So the question is, with this explanation that F stands for box fight and B for ballet, which of these players you think would correspond to a woman? Who is woman? The row of the column? The column. And the explanation is right, because the woman prefers, according to this story, a ballet. So she would have a choice between ballet and fight. So she will end up, if both of them choose ballet, then she prefers then the partner to go to ballet. And the idea is that if they both decide to go to this box fight, then he gets 2, she only 1, so is less satisfied. But there is an important assumption that each of them still prefers to go even to the less interesting event than to go separately. That's why for these other options it's 0-0. Now, does this game have a Nash equilibrium? You note, yes. No, but the question was, is there a Nash equilibrium? And how many? Second chance? 2. And the idea is that the 0-0 is never a good outcome, but these 1-2 and 2-1 are equally good. The question now, of course, arises which one to choose, and there is a problem. And this is an example of a game with 2 Nash equilibria. And this is to show you that it's not so simple, that if a game has Nash equilibrium, then we know what to do. This is a standard example of a game where there are two Nash equilibria. And if you compute the mixed extension of this game, you get a third equilibrium. And this, I just diverge. There is a theorem that in many classes of games, the number of equilibria, if it's finite, it's odd. So it's called odd theorem. So this you can, by calculation, establish. Okay, but anyway, it is just to show you that there can be one, two, more non-equilibria. So here is a new game. I hope you'll be interested in it. There are two travelers, and it turns out that both of them lost a suitcase. So they go to report, and each of them claims some money. So, of course, these travelers would say, my suitcase was extremely expensive. Let's say, suppose that 100 is some very high price for suitcase. So he says, I really lost 100 euro, so please reimburse me. And there are two travelers, they both would say the same. So now the traveling company, or let's say the airline company, came up, perhaps a lot was it, with an ideal proposal or the idea that they will say the following. You both report the loss of the suitcase, but now we will pay according to the following scheme. If you report the same value, let's say suppose that the cheapest possible is 2, maximum 100. If you both report the same value, you get it. But if you report a different value, then we do the following, because you had identical suitcases. We choose as the price of the suitcase the one, naturally, which was lower of the two reported prices. And additionally, the person who reported the higher price has to pay a penalty of €2 to the other one. You got it? Okay, so here is the definition. If they both reported the same, they get this value. If you got the smaller value, reported smaller, then you get your amount and also €2 from the other person. And this person gets the smaller amount minus 2, because he has to pay the other player. Yes, so this is clear. Now I have a question to you. What are the Nash equilibria in this game? Yeah, so that's the problem, that this is the only Nash equilibrium. And you can easily check it by studying any other outcome and see that there will be always one player who is not satisfied. For example, suppose that both say it was 100. Can you do better? Is there a player that is symmetric, so both of them should be doing better? So what is a better strategy than 100? Exactly. So then one of them says, oh, sorry, I meant 99, and he gets 101. Yes, payoff. So, but you can make it more systematic, and you will see there is only one Nash equilibrium. So by this simple trick, if you have rational travelers, then it will turn out that they would have to report actually the minimum value if they proceed as rational players. And this example was invented by an economist, Basu, from Cornell University, to show that there is a shortcoming in game theory, that the Nash equilibria do not predict how people behave. And in fact, he proposed this game to people of the Society of Game Theory, and it turned out that the sort of average value was in the 90s. But this shows that this Nash equilibrium as a predictive power has some limitation. But at least you are, a bit surprised that that's the outcome. Now, another game. This is a strange photo. Namely, I found out that on the island of Maldives, there is a beauty contest. Of course, it should not be sexist. So there is a beauty contest both for boys and for girls. And they perform together on stage. And this was the photo which I found sometime. Now, what has it to do with the course? There is a game called Beauty Contest Game, which is the following. It was proposed by and economist Moulin in '86. So the idea is the following. You can choose a strategy among a number 1 between 100. Now there are more players. In the example, there are 3. And the payoff is computed as follows. So there will be only one winner, or let's say more, but then we split the award. So the award is just one, say 1 million. And we have the following rule. We choose 2/3 of the average. And then we check who is closest to this 2/3. So the idea of the game is the following. Each of us reports a number. So I added this 20 example, 29, 32, 29. The average is, of course, 30. 2/3 of the average is 20. So in this specific case, the winners are the first and second player because they chose the number closest to the 2/3 of the average. Now the question is, what are the Nash equilibria in this game? Yes. And there are various ways to prove it, but the best way is to learn some techniques which I discussed in the lecture notes you will have, and some of these criteria very easily apply here, and then you have a kind of elegant proof. But what is the origin of this name? There was an economist, John Maynard Keynes, who said that the stock exchange is a beauty contest game. Namely, the idea is that you don't choose the shares which you think are the best, but which you think everybody is convinced that it's the best. So in other examples, suppose that there is some music context, say Eurovision, and the rules are changed that you will be a winner if you everybody can vote, and if you selected the winner. So the right strategy is not to choose the song or the singer whom you liked most. You should choose the singer who you think that other people or all of us consider the winner. So you play on what the others actually are choosing. You gamble on the other choice. And in this game, it is formalized by saying that your strategy, you know the game, the strategy is such that it should be closest to the 2/3 of the average. So you have to, so to say, put yourself into the head of the other players. And because of this nasty 2/3, it turns out that it is only one is the only solution. So I show you these games to explain to you some paradoxical outcomes. But now I will show you some other games which provide some better understanding what happens. And there is a concept which in economics people call common resources. We know what it is informally, but they even have a kind of definition, which is here. These are goods, so products which are not excludable, everybody has access to it, and are rival. So if one person uses, the other one is worse off. Example, highway. Let's say, suppose it's a free tollway, so free road. So in Holland, all the highways are free. So I am kind of, I do not know the concept toll road. It's kind of unknown. In Poland, are there free highways? Is there any free highway? Yes. Okay. So the idea is that it is everybody can use it at no cost, but if you use it, it affects the others. And there are many examples. For example, fishing. Every country is free to fish wherever it wants, seems so. So it is good which is not excludable, but it's rival. If you overfish, then the others are worse off. So there are plenty of these things. Also pollution is a good example. Many things which we all share, we have access to it, but if you use it, it detriments the benefit or affects the benefit for the others. And there is a problem here that if you overuse these common resources, it causes problems. For example, did you know that nowadays, if we look at what people eat in terms of fish, then people eat more fish which are farmed than they are caught in fresh water. So this is because of this overuse of these common resources called fish. And there was already early on a problem identified, which is called tragedy of the commons by a sociologist, Harding, who stated that if you leave it as it is, then things on their own will lead to a situation that we will overuse the resources and it will cause a problem, tragedy. Now, what is commons? Commons is a strange word. It comes from English. In Middle Ages, villages had, of course, people had private ground, but also there was public ground, say in the center of the village, and you were allowed to bring there your cow, that it would graze there. And this place was called commons. So it's a tragedy that if too many cows are brought there, then the grass will be eaten and it will be forever lost. So I will discuss now two ways to formalize this, are admittedly artificial ways, but which will illustrate the problem. So here is an example from a book by some economist, Gardner, who, by the way, was a chief economic consultant of Yushchenko, if you still remember such a prime minister in Ukraine. So there are two versions of this game. One is discrete, the other continuous. So here, use a resource, so you put the cow on this common meadow or not. So one is you put the cow, zero you don't. And now the payoff is very artificial, but it illustrates certain principle. If you do not put the cow on this common ground, on common meadow, then you get 0.1. And if you do put, it depends how many cows are there. So this M is the sum of the number of the cows which were brought there, because one is that you put the cow there. So M is the sum, so the number of the cows which are put there. And there is some artificial function, and you get your fraction of this. You are one of these M people. And this function has a certain property, and this property is in the second bullet, is such that this payoff goes down. So if there are only 9 cows there, then you get payoff 0.2. If there are 10 cows there, then your payoff becomes 0.1. And if there are 11, you get 0. So the more, and then if it continues, it gets negative, because this function is, as you see, the m square is preceded with a negative number. So what happens here is that this function regulates what is the payoff to people who put a cow on this meadow, on the commons. If there are too many, it starts to be a problem. But if there are few, then it's better. Because, for example, if there are only 9, then you get 0.2. Whereas if you don't put a cow there, you get 0.1. Question now is, what are the Nash equilibria? And now it turns out that if there are less than n peasants with this cow, then if each of them puts a cow on this meadow, then this is a Nash equilibrium. It's better for them. But if there are more than 10 or more, then the only Nash equilibria are if there are 9 or 10 cows which are put there. And these are, so to say, possible outcomes. You would have to say, I don't want to argue how you choose those 9 or 10 people, but these are the outcomes which the Nash equilibrium would predict. But now you ask the question, what's the best for the society? The best for the society is that you go back to the definition of social optimum. So you add all the payoffs, you get this social welfare function and you want to maximize it. So you have this SW function, which is the sum of the payoffs, and you choose its maximum. It turns out that the maximum is 5, which means that there are 5 people, if they use the resource, it's best for the society. And there is here this discrepancy, which shows that everybody would like to use this meadow because it's for free, but if everybody uses, it's very bad for everybody. And in fact, we can even quantify here, because of these artificial numbers, what happens. Another example, which is the game, which is Tragedy of the Commons, but in a kind of, how do you call it, continuous setup. So think of it that there is a building with, I don't know, 20 tenants, student dormitory, and there is internet connection. And everybody says, great, we get a free internet connection and so on. But now, if everybody uses this too much, like if everybody uses, let's say, to download some films, then it all breaks down. Sounds familiar. So now, how to formalize this? So we formalize it as follows. Strategies will be a number between 0 and 1, which will be what is the percentage of this, say, bandwidth of this internet you claim for yourself. And the payoff function is constructed in such a way that you get, if SI is what you choose, your percentage, then intuitively you get better off if you claim more. However, you are negatively affected by what everybody claimed. So if you see SI is multiplied by a number where the second term is negative. So the more people claim, the smaller this 1 minus this number becomes, and it can be even negative, and as a result, it pushes down your satisfaction, so payoff. So this is, and when everybody claims 100%, then that's it, you get 0. So this is the outcome of this. So you can get here, either if you choose the resource, then it's this top outcome, but if people claim in total more than 100%, everybody gets 0. And you can ask yourself, what are the Nash equilibria? And it turns out in this game that you get a situation where you have several Nash equilibria, but a more natural one where it is symmetric, because this situation is symmetric, is where, and this is a bit surprising, each player claims not 1n, because then remember the payoff would be 0 for everybody, because n times 1n is 1, so they would get 0 according to the payoff function. No, the optimum, the Nash equilibrium is obtained where everybody gets 1 over n minus 1. So when they use it, still there is 1 over n minus 1 left. And the social welfare of this is obtained there. It is this function here, the n divided by n plus 1 square. You can also ask the question, what's the, social optimum in this game? And the answer is completely different, namely when they together claim 50%, no matter how they divide it between themselves. So what happens is that when the sum of these percentages is 50%, then the social welfare is 1/4, and one can always show that it is always the case that for Nash equilibrium the social welfare is smaller. And in fact, what happens here is that when the number of players increases, then the social welfare goes down, and the usage of the resource leads in the limit to 100%, whereas the social welfare, the optimum, never changes. It is just 1/4, and the usage of the resource is 50%. Now, what do these two examples suggest? They suggest that using the concepts of Nash equilibrium and social optimum, we can talk in a meaningful way about issues which sociologists identified, and they pointed out as a danger to the society, that we overuse our resources. This analysis suggests that this happens because of the, so to say, hidden strategic game which is built into this interaction, and that this interaction leads to two different outcomes. One, when we focus on Nash equilibrium, and remember, in Nash equilibrium each player said, yes, I am satisfied with the outcome. So they, in their small universe, say each of them is satisfied, whereas on the top level, the person who looks at the society say, no, it's bad for the society, you should do something different. So just to recall, here the optimum solution was put 5 cows on this meadow, whereas in the Nash equilibrium it was 9 or 10. And here it was the same. The idea was that each person would claim 1/n+1 of the resource, and in total they would claim n/n+1, whereas the optimal from the society point of view is that it should be half. Okay, so this shows that using these two simple concepts, you can explain certain phenomena which appear around us, and you can talk about this more meaningful than some kind of vague claims that it's not good for us and so on. And there will be more such examples. So now I have an example which I mentioned before, this Cournot. Cournot came up in 1838 with the first example of a game. He, of course, didn't understand that it's a game, but he took an interaction between producers, and he came up with an analysis of this which explained how pricing arises. So the idea here was, there is some, of course, here simplification, because the product is now infinitely divisible. So let's call it oil, okay, that you, and not, let's say, how many television sets to produce. And there are n companies which simultaneously defined how much to produce. So think of the OPEC consortium of the countries which produce oil. And natural assumption is that the price decreases in the output. So the more oil produced, then the price is lower, logical. So we try to formalize it using a game. So this infinitely divisible product, it will be just, you decide your level of production by choosing a number, a positive real number. It will be your production level. And then there will be a price which will be determined by how much is produced. So the price is put in red, and you should look at it as follows. There is some fixed, so to say, number, A, and now you deduct something which depends on how much oil is produced. The more oil produced, the price goes down. That's why this B is positive. And this depends negatively, this red expression, from the sum of these SIs. So as a result, if we know what is the price of the oil, then how much does a given producer gain? Well, we multiply how much he decided to produce, which is SI, it is his strategy. We multiply it by the price of the oil, and we deduct his costs. And the costs are linear with respect to how much he produces. So this CSI are cost of production. And this is the payoff function. So this payoff function, in some sense, provides, formalizes the intuition that the price goes down when there is more oil, logical, and also how it is how those players, so the producers, depend on each other. Because the payoff of each producer, obviously, by definition, depends on what the others produced. So what we have now is a game, so it is natural to think what are the Nash equilibria. And it turns out that this game has a unique Nash equilibrium. This will be a good exercise for you at home. It is all worked out in lecture notes, but it is based on first year calculus. You just compute a maximum of a function by taking the first derivative, and the function is a square function. So it is really very simple. You obtain a unique Nash equilibrium, which is some number. It doesn't matter what is this number. But this number determines the price of the product in this Nash equilibrium. And the price of this product is determined by plugging in these values, these SIs, in the price of the oil, which was this red expression. We now have a unique Nash equilibrium, which says each S1, what is its value. We plug it in this red expression. A and B are given. We get a fixed number. And it turns out it's some number. It doesn't matter, because I want to, on the next slide, explain what these numbers imply. So I repeat here, the price of the product we can determine in this Nash equilibrium. And we can also compute, because we have the payoff functions, and now it's again an exercise in first year calculus, we can obtain what is a Nash social optimum. And then we can compute what is the price in the social optimum. And the price turns out to be different. And then there is a certain assumption which was before, now it starts to be relevant. Under assumptions with these numbers, the price in social optimum is always bigger than the price in Nash equilibrium. So what does this, don't look at the numbers, just remember the message. The price in the social optimum for this game is which is this, A plus C divided by 2, is always bigger than the price in the Nash equilibrium. Now, the price is bigger, so we somehow are worse off, you would think, because we wanted that things are better in social equilibrium. But the point is, it depends from whose point. If you look at the customers, then in social optimum, the price would be higher. So this is not good for customers. But in Nash equilibrium, the price is lower, so it's good for the customers. So what does it mean? That it is good to have a competition. Because if there is a competition, they will compete and hopefully Nash equilibrium will emerge. And Nash equilibrium delivers a lower price, which explains in an informal sense why when there is some project you have always you write out an open competition and companies can, let's say, subscribe or apply to, I don't know, build a bridge or even, I don't know, prepare a meal for a conference as it is here. So the outcome is that the competition drives the price down. And this simple observation, which, so to say, everybody intuitively understands, can be formally expressed using this type of computations. And this I illustrated only on this oil, but there are many variants of it. So what happened with Cournot is that he proposed it in 1938, but he proposed it, if I remember, only for 2 players, and he computed the Nash equilibrium in this game, which was not difficult, but it was completely new that you could provide such an analysis to give some formal meaning to some intuitive ideas. And this was generalized in many ways, and it goes on. It is a story which is now, what, 180 years old. So still, it is an ongoing topic because one studies various variants of it. It's one of the most, so to say, well-studied game or a variant. Every student of first year economics gets this example, and he gets some solution in some semi-formal way, and then as he progresses through the studies, he gets a more formal exposition, which is the one which you will find in the notes, which is still very elementary, but it connects economic intuition with formal reasoning. Okay, so this is the end of what I wanted to tell you today. So I'll summarize what I did after the break. I tried to show you some examples of interesting games. In each of them, I showed you that there is a difference between social optimum and Nash Equilibrium. And in fact, in strategic game, the tension between these two is the most fundamental and driving force behind this whole area. And I'll return to this tomorrow. So that was all what I had in mind for today.